All right. So your lab number 5, just don't forget, it's due next week. Just check the deadline and don't miss it, right, to claim your credit. And meanwhile, make sure you study the background information and then do the stuff. And then I'll release the solution right after the deadline. So you can also study that and ask me questions later. Your written test number 2, the result has been released on eClass. And if you want to go over the question with me, just drop by the office hour. I still have today, 7 p.m. and also next week, the usual time. Okay. Which means Monday and Tuesday. But starting from Wednesday, I might have different hours for Q&A, but I'll let you know. And for your exam review, just make sure you indicate your availability by the end of tomorrow before the polling closes, and then I'll confirm the time pretty soon, okay, based on everybody's preference. I'll try, right? All right, for the data sheets, just to let you know, now, relaxed. Handwritten is fine, all right? So if that makes it easier for you to gather information, be my guest. Handwriting is fine, screenshot is okay. If you want computer type, that's also fine. Basically, no restriction. However, make sure the font size, all right, guys? Please don't make it too small, all right? 10 pt, all right? That one will be strict. And one-sided, no exception, okay? One-sided. I think that'll be it. And other exam information, you can check the recording from Tuesday. I also spoke about it. And then you can ask me more, maybe during the exam review sessions. We can also talk about it. I plan to schedule maybe 2 of them. So you can join either one or both of them. It's up to you. Of course, I'll try to record it so everybody can get access to it as well. All right, any questions about the course? Yeah. Yes, fully handwritten. No margin. Okay, everything I said on Tuesday applies, except it's now you can also do handwriting. Not a problem. Okay. We'll see how that goes for this year. If that's really terrible for everybody to be handwriting, then I'll change that next year. But for you guys, it's okay. Let's do some experiment today, this time. All right, I will make sure these policies are written down. I'll release the PDF, the guide, but everything will be consistent. There should be no surprise. So you definitely can start working on your data sheets and go over the examples. Okay. Go over the study materials. All right, so we got 2 more lectures for this course, and I think we definitely just want to finish off the bridge controller. And the refinement that we introduced last time, M2, is the last refinement to study. And there are just a few topics that are a little bit tricky that we just want to go slowly, just to make sure you can follow them through. And then sometime next week, I'm also going to release some example questions for you guys to practice about the exam. Some. Okay, but of course, your priority should still be go over all the materials. That's really important. Okay, recap. So from last time, I think the biggest topic was about relative deadlock freedom. All right, so the details, you should definitely go over the notes, go over the slides, and check the recording if necessary. But quick highlights about what we spoke about. Number 1, you want to compare the relative deadlock freedom proof obligation, which only exists in the context of a refinement model, versus if you talk about guard strengthening, which is also another refinement condition, right? So you can see that just seemingly they seem to be very confusing. One of them, in the guard strengthening case, you see the concrete guard implies the abstract guard. And in the relative deadlock freedom, you see abstract guard implies the concrete guard. However, as I said before, the critical difference here, in the guard strengthening case, you're talking about individual events. But here, you're talking about the disjunction of all the events in a particular model. So that's why the implication here is not exactly consistent. All right? That's something you want to keep in mind. But I would suggest when you actually study about this part of the material, you want to go back to the very intuition about each one of them, which I spoke about in detail in the class, right? That's something you want to go over. And then, compare these two, the proof obligation, and go over the principle about why deadlock is really bad. We don't want to introduce any deadlock scenario in the concrete model. That's really the principle. And convince yourself why this one here is really what we are aiming for, as opposed to something like this, where we can find some weakness which represents some new bad behavior of deadlock has been introduced to the concrete model, right? That's also something we went over from Tuesday. Well, quite much information in this page here. That's why we spent so much time on Tuesday going over. So please study that carefully, and then get ready for whatever question that will be on the exam. Okay. All right, and then we talk about, just take this proof obligation here, and then we try to formulate it, and the formulation itself will be pretty straightforward. Basically, just have to disjoin all the guards from the concrete model, and just don't forget, not only that you have to get all the old events, but also all the new events as well. All the guards, just don't forget, all right? So you can see these are all the guards from the concrete events, old and new, versus the disjunction of, over here, the disjunction of all the abstract events over here, the guards, right? That one, of course, has no new events in the abstract model, all right? Okay, that's relative deadlock freedom, and the proof itself will be some exercise for you, okay, to really go from the very first, the very beginning proof obligation, you want to go to some intermediate one and complete the proof, right, as I explained last time. And here I'm giving you some hints about what rules you may want to use, but as you practice, maybe closer to the exam, try to redo it without any hints about what about what inference rule you should use. I think that'll be more like a closer to simulating the actual exam, because I may not give you any hints about what inference rule you have to use. Okay. All right, so that's about relative deadlock freedom, and that's a summary about the between the two models here that we talk about, M0 and M1. And just remember, these are the list of criteria for proving that the refinement is actually correct. We'll talk about guard strengthening, relative deadlock freedom, compare these always, and also invariant establishment versus preservation, and convergence, which means lifelock. All right. Also, you want to compare and contrast what's really deadlock and what's really lifelock. Okay. And specifically for measuring the presence of lifelock, we use the variance. Okay. Just don't forget. We also spend quite a bit of time talking about it. And then we started the final refinement, which will be the second refinement. So we got M0, M1, and M2. And there is a special scheme that we're introducing called superposition, meaning that in the concrete model here, we are using not only the new variables, which are the two traffic lights, but also the variables that we kind of inherited from the abstract model, M1. So we got a mix of the abstract and concrete variables in this new refinement. That's called superposition. All right, so if I refer to superposition in the exam, you should know what that really means. Okay. All right, so as we will see today, the events, which we haven't really got into, but we will today. So when we talk about the guards, when we talk about the actions, we're going to have to worry about A, B, C, and MLTL, ILTL. So these 1, 2, 3, 4, 5 variables. And of course, you can also look up the environment constraint that we're dealing with in this last refinement. All right, and I believe, so that was the last page that we spoke about, which is about formulating the invariance. All right, that one there shouldn't be too strange. So we are basically saying what happens, what does it really entail when MLTL is true, meaning that this part here is green lights. And what happens when this part here is green lights? So the idea would be when there is a green light over here, ML out is enabled to actually occur. I will make it a little bit more precise in just a moment. And symmetrically, if there's a green light, sorry, it looks like a red, but imagine that's green light. If the light here lights up green, then that means IL out is also enabled. That means some car can follow the lights and pass through to the bridge. All right? And it's very critical to realize right away. In this new model here, for MLTL and ILTL, whenever you turn the light to be red or green, you have to make sure you can do that when it is safe to do so. For example, I should only make this light here, right? I should only make this light here green if, for example, there is no car going this way. And also, the number of cars in the bridge and the island have not reached the maximum limit just yet. Otherwise, going out another car by ML out is going to exceed the limits, right? So these are the kind of concerns we have to deal with, right? Just remember. Well, we're going to make it very precise once we talk about the guards and actions. All right, that's the exam information, but just remember, this right here, no longer valid, all right, as I said, right? Don't get confused. All right, guys, any question from last time before I talk about some new stuff? Good. All right, so now let me give you some very quick intuition about the events that we're dealing with in this new refinement before we work out their guards and action. That'll be easier for you to appreciate what's going to happen. All right, so we got we got A, B, C here. We got MLTL, ILTL. Okay. You can think about A, B, and C. So these are more of the computer variables. They are more like a global, like a sensor that will tell you what exactly are the number of cars on the bridge. Like A, how many cars on in the island, how many cars on the bridge, going the other way. Right? So let me just write down two Lincoln notes for you. So A, B, C are computer variables. What does that mean? That means drivers, individual drivers, should not be aware of these variables. Drivers should only follow through green light, red light, nothing else. Drivers should not be bothered, should not be concerned, or should not know. Should not access their values. This is a very important reality reflection we need to have in this refinement. So let me show you something right away. When I say drivers over here, so drivers' behavior are represented in our model by two events, either ML out or ML in. For example, sorry, ML out, IL out. What I mean is, so this one here will be ML out, going out of the island, versus IL out, going out of the, going out of the mainland, also going out of the island. So these two events really represent the behavior of the driver. The only thing they should be concerned about is whether the light here is green or red. That's the only thing. So let's now have a very quick check back to our M1, the original model. I want to show you that the original model that we had mathematically is valid. However, it's not really reflecting the reality because, let's take a look. If we go back to the summary of the original model over here, right, M1. Okay, let's take a look. The ML out and ML in. So these two events, as I said, ML out and IL out, these two, all right, these two. These two, as I just mentioned, they are more like a driver's behavior. In order for a driver to really go onto the bridge outside the, out of the mainland, the driver somehow need to know how many cars are on the bridge. The driver should know how many cars are on the island. They also know if there's any car coming over. Should they know these details? Realistically, no. But in that simple model like M1, the abstraction is too much to be realistic. So that's why in M2, we want to somehow factor these out into different events. That's a very important insight for you guys to realize. All right, let me say that again. In M1, having this mathematically is valid. However, it does not really reflect the reality because for individual driver to decide whether they are going out of the mainland, they should not be bothered, or they should not be even know about how many cars are on the bridge, how many cars on the island. I should not be concerned. For me to go outside the island, I only check the traffic lights, green or red. All right, that's important. So that's the kind of reality we want to reflect in this new model, M2. All right, let me write down this remark, and then I'll show you something here. Drivers should only be concerned about traffic lights color. Right? Mainly whether this one is green or red and whether this one is green or red. That's it. All right. So I want to make some contrast to show you right away, and that will kind of illustrate a big picture about how we figure out the guards and actions for M2. Okay. Now I'm going to make some reference to M1, but you can also look back yourself. Okay. I'm going to make some example here. Let's say ML out. Okay. let's say we got M1. That was the first refinements. And also we got our M2, the current refinement, which is second refinements. Okay, we got a second two refinements. And for the first refinement, if you recall, we don't really have the traffic lights. So basically, when you got a main lane here and you got a bridge over here, so the only event you can use to represent the system is ML out over here. That was the only events. We don't really have anything else. There's no traffic lights. On the other hand, for the second refinements, we still have the main lane here. Main lane. And then we have our one-way bridge here. And now the complication is we have traffic lights here. All right, that's our traffic lights. And MLTL. Right, so that's the extra concreteness we have added. Right, so here there are two events we have to watch out for the new refinements. We still have ML out. Let me still put it. We still have the ML out. But there is another new event in this model, which is called MLTL green. You will see that later, okay? I'll just write it down first. There is another event called MLTL green. And the event is very simple. If the event is enabled, that means it will be safe to turn this traffic lights, MLTL, into green. That's it. All right? As simple as that. So we got this old events over here. We also got this new events over here. We got two events. Okay? Just understand that. And what about the guards? If you look back to the ML guard, I'll just put it here for your reference. So for ML out, it has the following guard, which represents when it will be safe to really for the car to go out of the island. And that one there has the guard. Oh, sorry. That one has the guard over here. Okay, let me see that. It will be A plus B less than D. And also C is equal to 0, right? That one we discussed already, so we can leave that. So this one is basically the abstract guard. But now, ML out over here has the guard. But ML out over here is no longer going to inherit this guard, because the ML out here, as I said, is a driver's behavior. Driver should not be concerned about A, B, and C. So what we will do instead is to shift this guard over here into this new events. That event tells you, you can think about MLTL green represents a computer sensor behavior or actuator. When the system variables A, B, and C are such that it will be safe for the light to be turned green, then this event can occur. Right? So think about this is computer, this is driver, separate. So this clear separation is another concreteness we have added to this model. So that's something I want to get very clear in the at first. All right, so this guard over here is going to be pushed. Okay, so this one is going to be pushed to the guard of new events. MLTL green. That's something you will see. All right, so this is important for you to note. Otherwise, when you study the actual model on the slide, you might be confused. Why are we suddenly pushing this guard into MLTL green, but not ML anymore? Right? Again, it's because we are now trying to separate between computer program and also human behavior. So that's an added concreteness in the refinements. And what about the guard for ML out? Very simple. The driver simply follows the traffic lights. So ML out will only be allowed to really happen if this light here is green. Okay. So this is something to add here. So the guard over here for ML out is going to be MLTL is equal to green. So we got separate guards. All right, any questions so far about the separation? Right, question, please.
Is it always the case that you
Absolutely. So think about we always refinement goes like from more abstract to more concrete. More concrete, that means you're getting closer to the reality. The closer you are to the reality, the more detail you need to introduce. That means the more complication you have to deal with. Yeah, we do like a one level at a time. Yeah. Yeah.
This graph, a plus b less than b
Yep.
and
Mm-hmm.
c is equal to 0. This is the card for MLTL green. So MLTL green is a event,
You say
right?
new events.
Inside
Yeah.
MLTL.
Okay, sure. So in the M1 that we finished on Tuesday, that one there doesn't have the MLTL green. That one there only has ML out, for example. So now we somehow want to separate ML out into two events in the refinements. Think it that way. Not really exactly splitting, but think about we are adding some concreteness to separate between the two. Okay? So now ML out here in the old model somehow doesn't distinguish between computer behavior and human behavior like a driver. But now we do distinguish between them. So ML out right now in the new model is the old events that's going to represent human behavior only, which means a human only follow traffic lights. They are not aware of any system variable like this. Okay. On the other hand, this will be the new events called MLTL green. There's another one called ILTL green, another one, so pair. So this event here is only exists in M2. It's an events. It's also an event, which we'll see a little bit later. Now I just want to give you like an overview so you can see the overall picture. Yeah. So this is an events as well, which only exists, only get added in M2. Yeah. All right, that's good. So now let's now talk about this particular trait just to have an idea about how these events are supposed to be put together. And then we're ready. And then we'll be ready to go over the guards and actions for all the events. All right. So let's say we got some initialization. Let's say no cards whatsoever. And before you actually got ML out, you're supposed to turn the light green. Let's say in the beginning, let's assume. After inits, basically, the MLTL, ILTL, both are simply just red in the beginning. And then MLTL green is enabled because there's no car coming from the island side, and also we haven't exceeded the limit just yet. So this one here can occur. So what's going to happen is we're going to somehow have MLTL green. Number one, it's going to happen first. All right? And then as soon as this is turned green, the driver who's waiting can actually now follow traffic light and go ahead. So that will be the second event, ML out, right? So that will be number two. All right, let's say this particular car goes into the, and of course this car will actually go into the island. When you go into the island, we have already done the safety check already. So it's okay, just go in, ILN. Okay, so we got, sorry, let me just turn it off. Beg your pardon. Okay, so we got here ILN. This will be number 3. All right, and then let's say this car maybe stay around in the island for a while, and then now they want to go out. Before they can really go out, presumably when this is green, this should be red, presumably. Okay, so it's going to wait until this one also turns green. It's going to wait. And just remember, when this turns green, the correct behavior should be this one should also turn red at the same time. We'll see exactly how this is going to work, exactly, but conceptually, right? So once this is actually turned green, the way to turn the green is by ILTL green. So that's another new event. So this one here is going to be number 4, ILTL green. So once it is turned green, the driver can now just follow. Okay, IL out. Now they can go out of the island. And then this will be number 5. And then once the driver gets close to mainland, we have already done the safety check when we try to turn this traffic light green. So driver can just go back, not a problem. All right, so finally, we have the events over here. Number 6. Okay, that would be ML in. Okay, so that's kind of like a typical sequence we can expect. Of course, there might be some interleaving if you got multiple cars, but that would be the typical one. Okay, so that would be number 4, and number 5, and then number 6. All right, any question before I make a final remark about this? Yeah. Yeah, exactly. So what we just illustrated over here, very quickly, you'll see that on the slide as well. What we just did was ML out is going to be just of the guard, MLTL equals green. Similarly, the IL out over here, the guard will just be ILTL equals green, symmetrically. And then when we talk about ILTL green, we also need to safely check if it is safe to do so. For example, A here should be equal to 0, just like how we did a safety check for the MLTL green. Question? Sure. Mm-hmm. That's something we'll do separately because now, okay, remember this the big picture. If you think about how we prove M1, the first refinement we actually proved correct, right? The way we did it was we got to make sure every old and new events will preserve and establish the invariance. We'll do something similar as well, right? So here we talk about the updated ML out and also the new event MLTL green, for example. So we still got to make sure each one of them will establish the invariance and also maintain the invariant as well. That will still be something we got to do. So that's why, let me say it again. If you look back to this picture here, right? When we go from M0 to M1, we had to prove all these safety criteria, like a correctness criteria. When we go from M1 to M2, we also have to do these as well. Okay, just don't forget. All right, any other questions? Good. Okay, let me make a final remark, and you can also keep that in mind when you review the notes. So when you look at the new refinement here, just remember the only 2 events that we are trying to do safety check is when we decide to turn this light green, and also when we decide to turn this light green. So these are the only 2 events where we do some safety check, like things like here. Just remember, okay? I'll do that. So only 1 and 2, right? 1 here and, 1 and 4, beg your pardon. Only 1 and 4 require safety and capacity check. Capacity. Yeah, safety check like C is equal to 0, and capacity check like this. Okay? Only 1 and 4. Before we turn the corresponding traffic light green. And of course, when you turn one of them green, the other one should be turned red at the same time. That will make more sense. Okay, so if everything's good, I would suggest we try to work out exactly I'll go over with you the actions and guards for all these 4 events. So in the next 2 pages, let's now go over number 1. We're going to look at ML out, and also IL out. Look at these 2 first. And then we look at MLTL green and ILTL green. For ILN and MLN, they remain the same. That's why we don't mention them. Okay? Let's now take a look. All right, let's now talk about ML out and IL out. So the action here would just be the same, right? Because a car going there, we should really update the action, right? All right, so now what should we put for ML out? Well, after this intuitive, kind of sketch over here, ML out represents the driver going to obey the traffic lights. So the only guard that we need would be here. So this one, the only guard that we need to have is MLTL equals green. That's it. As simple as that. Symmetrically, for IR out, it will represent a driver drive through from the island onto the bridge. Then that means ILTR must be green. So ILTL equals green. And the action part over here to update the counter will just be the same. So by the way, just in case you're confused, when I talk about human behavior, I'm only talking about the guards over here. So this tells you drivers will only obey the traffic lights. However, when you do the event actions over here, this will still be done, right? Just about updating the number of cars. It's not really done by the driver, but just going to be updating the system variable. So it's different. All right, are we good? So very simple. But of course, in order to really understand why we need such simple guards is to really see that we are now splitting between these events and also this event. That's added concreteness for the new refinements. Yeah. Of course. Yes, correct. So you can think, oh, that's something we'll get more into. So we can be sure that ML out, we can be sure ML out and also IR out will not be enabled at the same time because they depends on whether or not these two are the green at the same time. Okay, let's understand that. Okay, but it turns out our model at the moment is not 100% correct, which we have to go over some proofs and see. Okay, so what you guys need to understand now it will be, in order to make sure ML out and IR out cannot really occur at the same time. These two lights cannot be green at the same time. Should not be. But it turns out it's possible at the moment. So that's why we've got to fix the model in just a moment. Okay. All right, so let's now make a remark. So it's a very simple observation here. In order for these two events not to be enabled at the same time, both traffic lights cannot be green. Right? Simply because of the guards we have. All right. All right, let's now move on to MLTL green and also ILTL green. So these are the critical events in this refinement here. Again, if you look at the diagram here, MLTL green, ILTL green. So these are very important events to enable because once we turn the light green, driver is going to follow that. All right. So that's why we got to do all the important capacity and safety check in these two events. Right? And now I can put it. Let me start by putting the one we just spoke about. There will be one minor extra thing we got to put as well, which makes sense, but just in a moment. So I'm going to put number one, A plus B less than D. That's about the capacity, right? In order for this light here to be turned green, I want to make sure the capacity is enough, right? If we try to add one more car to the bridge. And also C should be equal to 0. And make sure no opposite traffic. Let's put this for now, just for now, okay? Symmetrically, if we want to work out the guard for ILTL green over here, we got to make sure in order to turn this light green, we got to make sure there's at least one car in the island. And also the opposite traffic should be no. All right? That means we're going to put B larger than 0, also A equals 0. And one thing for you to really go back and verify, so this one here and this one here, okay? You will check to see. This one here is the abstract guard for ML out. Okay, I'm talking about M1. Okay, you can double check. So these are the abstract guard of ML out, in, and 1. Okay, but we shift them to here, as I explained earlier. And also, this one here are what used to be the abstract guard of IO out. In and 1. Okay, abstract and also abstract here. All right, there's just one additional thing to actually say. In order to turn this line green, I should only turn it to be green just once. Meaning that if the light is already green, I cannot allow MLTL green to happen again right away. All right? Well, simply means I cannot allow to say MLTL green to turn this green twice in a row. I should not allow that. All right? So the only scenario where I can allow this one to happen will also be MLTL is currently red, plus the constraint over here. Okay? So that will be the another guard. ML TL equals red. All right, this one here must be red at the moment, so I can turn it green. That's the only chance. I should not allow it to turn green multiple times, which is silly. All right, and then this symmetrically, this one here, ILTL must be red as well. ILTL equals red. All right, so these are the complete guards. And the action here should definitely make sense, right? I'll just turn MLTL to be green. That's why it's called MLTL green. Here I turn ILTL to be green. That's why the name here. All right, guys, question? Yes? It should be. It should be. But as we will go over some proof obligation, it turns out the current model contains some contradiction, which will allow both light to be green, which is not good. So we got to fix the model. Yeah. Mm-hmm. Mm-hmm. It will actually. You're going much ahead. Yes. Okay. No problem. So guys, just for now, since we gotta go through some like a process, but your classmate was actually quite right. Ultimately, we want to make sure when you turn this guy to be green, you better turn the other one to be red at the same time. That's something we'll see for sure. Okay? Yeah, for sure. We'll get there. But let's say the model is as is. We're gonna see that we're gonna run into some unprovable sequence at some point. All right. If no question there, I'll go over maybe maybe one more thing, and then we'll take a short break. Okay. And let's now talk about invariant preservation. All right. So let's say the one I want to give you as an example will be, let's say we want to specify invariant preservation here, and then invariant 24, which is this particular invariance. All right. That's one of the invariants we worked out last time. When ILTL green, ILTL is equal to green, and there's some constraint there. So that's what we are talking about. Okay, that's what we have. And guys, it will be up to you to double check this is the case. All right, please double check, right? We have done this many times. Check where the axioms are, abstract invariant, concrete invariants, and also since we are now talking about ML out. So this one here should be the concrete guards for ML out, which is here. All right, that one I can show you quickly. That one you can see MLTL equals green, so that's why you see MLTL equals green. You'll see that there. And then this is the part you gotta double check you can do. This part here, right, is about the invariance satisfying in the post states. And that one there, the answer should be over here. All right, but I can give you some very quick hints. If you look at this invariant here, okay, if you compare, okay. Now compare this one here, which is an invariant in the pre-states. Beg your pardon. So this one here, yeah. Let me do better. There we go. So this is the invariant satisfied at the pre-states, and this is the invariant satisfied at the post-states. If you compare these two, the only difference is you can see A plus 1 over here as opposed to A. That's the only difference. And the difference comes from, since we are talking about ML out, if you look at the ML action, you only say A should be replaced by A plus 1. That's why you see the A here is replaced by A plus 1 here. That's the only thing about before after predicate. All right? But of course, in the actual, maybe in the exam, you want to make sure if I simply say now, formulate the proof obligation for this particular sequence, then you should know how to do it, especially calculating the relevant invariant satisfied at the post states. That's something you got to make sure you know how to do. Okay. All right, any question? Yeah. Yeah. There we go. Yes. Mm-hmm. Yeah. Yeah, okay. We are kind of, you guys are thinking ahead, which is nice. Okay, at the moment, you're right. At the moment, these two events are not really specified correctly, which we're going to fix once we see the unprovable sequence at some point. Okay, but you're quite right. The correct action should be not only that you should really turn this light here to be green, but also you should turn this light here to be red at the same time. But we are not doing it at the moment. So the model at the moment is not really 100% correct. Now we're going to go through the process to say, let's say we thought it was correct. So we're going to formulate the proof obligation, see the unprovable sequence, and we'll try to fix it. That's the process we're going through. All right. Very nice. Okay. All right, so please double check. You can do this one here. And then there is one exercise for you about formulating this particular invariant preservation, right? It's about invariant 2-3 here, and then IR out. I'll leave that to you. Yes? That's correct. That's correct. Yeah, so when you double check, you can definitely, oh, actually even put it here for you, right? You can see everything, all the labels are here. Double check, right? And of course, in the exam, you don't really have to put all these labels, right? We'll find out exactly what you should put, unless we say you have to do that. Okay. Another tip for you guys, actually, since you got limited space for your data sheets, right? If I were you, since so many proof obligations share very similar hypotheses, you don't really need to put it individually, which would be a waste of space. You may actually only put the ones, you may say something like a common hypothesis for all the proof obligation. And then maybe for invariant preservation, you have some additional ones. You put the additional one and also the goal. You know, something like that, right? Yeah. Try to be creative, right? All right, that's good. And let me do one more, and then we'll take a break. Just one more, please. Right, in order to discharge the proof obligation over here, for example, we're going to need these 3 new inference rules. All right? These are not too bad to understand. Okay, let's now go over them quickly. This one here, in order to prove this, it would be sufficient to prove this. And this guy here may look very familiar to you guys from lab number 4. Modus ponens. Okay, if no, that's okay. Let's now review it. All right, this one saying, if you got some implication to the left of the turnstile, in that way, you got P implies Q. And you also got the antecedents of the implication here also here. That means you can apply modus ponens. P and P implies Q is equivalent to just Q. That's what it is saying. All right, I'm going to write it down here. So you got to recall modus ponens. So basically P and P implies Q. And then that one there should really implies Q. Right? You know that. All right, so what we have over here is we got P, and P implies Q, and then we can conclude we got Q. All right, that's what we have. That's the first one. All right, so this one here is basically to say if you got implication to the right of the turnstile, you can simply put this P over here to the left of the turnstile. Because if you think about what's happening here, this guy here is formulated as H implies P implies Q. And we're saying that it would be just equivalent to H and P, which is like here, implies Q, right? It makes sense. So in order to prove this, it would be sufficient to prove this one instead, where we simply get the antecedents from the goal into one of the hypotheses. Okay? Okay, last one. If you got negation to the left of the turnstile, this one looks a bit funny. You can somehow put not P to as P as the goal, and put the Q as not Q as the hypothesis. Does this remind you of any rule that we spoke about earlier in the course? Not P implies Q, not Q implies P. Contrapositive? Agree? Okay, I'll write it down. So basically, we got something called contrapositive. So think about sequence is just a syntax for formulating logic. So what we learned from the math review lecture is still valid, right? So think about just this part here, right? This part here basically is not P implies Q. And then by contrapositive, we know that it's going to be not Q implies not P. And we know pretty well this one here, double negation, is going to be P. All right, you can see that's exactly the not Q here, and P here, right? Exactly. All right, so you just gotta know to use the rule whenever applicable, which we'll see. All right, so these are the 3 rules that you might find useful. If no question, why don't we take a short break? And alrighty, so before the break, we spoke about the 3 inference rule that might be useful for invariant preservation. So now we are now going to look at invariant preservation. Okay, so here is the flow. There will be a bit of study you have to also do offline. So I'm going to point out to you the high-level picture, so it'll be clear to you what to do. So before the break, we basically spoke about 2 invariant preservation sequence. One will be ML out invariant 2-4. The other one, which you will try to do, IL out invariant 2-3. So they are kind of addressing different invariants, just as an example. So these 2 are the more complicated ones. So that's why I want you to try those 2. So the next 2 pages I'm going to show to you, we will try to prove this one here and also this one here. So it turns out none of these is provable. And interestingly, when we reach the final sequence for each case where it's unprovable, they look similar. And that's where we're going to get some feedback and try to fix our model. So that's what I'm going to do in the next 15 minutes or so. All right. Again, just remember, in the next 2 pages, I'm going to talk about this here and also this here together. All right. So when you look at the slide, I'll show you very quickly on the slides. So let's see where we are in the slide. So that's what we covered before the break. Everything has been covered. All right, so this is the first invariant invariant preservation sequence we'll try to prove, number 1, also number 2, right? And by the way, that's the answer to your exercise about formulation. You can check, okay? And as we try to prove that, you also need a 3 inference rule, which we also covered before the break. And when I say first attempt, that means when we try to prove it the first time, we're going to fail. That's why we're going to fix the model somehow. and we get some progress done. All right, so this one here, somehow you get to some point that we're going to get stuck. Okay, so you can see question mark over here. That means we get stuck right here. So it's unprovable. So what I will do is I'm going to go over with you a little bit about what you should really we should really watch out for. The entire proof is something that you should really go over by yourself, but I'm going to highlight the ones that we are applying some new rules that we just learned today, so you can get a little bit more guidance. Okay, let's now take a look. So this is the actual proof obligation that we started with. Okay, you can see this one here is exactly this one here. All right, and we do some monotonicity, so we got this one here. All right, so here we are applying a rule called imprecation on the right hand side. That's something we just learned today. Let me show to you how to apply that quickly. Okay, so this is the sequence we have over here. So you can see we got some imprecation over here, ILTL green on. You can see we got, sorry, let me do it again. We got an imprecation here to the right hand side of the turnstile. So that's why we can apply imprecation R, in which case we simply put the antecedents as one of the hypotheses. Right? That's what the consequence will be if you apply that rule. So that'll be imprecation R. And for that one there, you see ILTL green is going to be moved to here. So it goes from here to the left of the turnstile. So that's the first one, right? And then you can see that here we got another one here, imprecation L. So this one tells you ILTL equals green. And also we got another imprecation in the hypothesis where the antecedent is exactly that, modus ponens. All right. So you can see here we got ILTL green implies, and also we got ILTL green right here. That one there, we can apply imprecation L. We got exactly the consequent over here. So think about this guy over here is put into here. So that's imprecation L. Okay, you got to look at it more closely when you study for the notes. All right. Okay, let me see what else. And that'll be it. Okay, everything else is something that we learned earlier. So you just want to make sure you understand the difference between imprecation R versus imprecation L. Okay? And then, and R is something we spoke about last time. So and R and also OR L are the only two rules that are going to split the sequence from 1 into 2. Right? That's also another insight you might have realized already. Right? So this is something we're going to run into as unprovable. All right? So this is the contradiction somehow, but I'll show to you. I'm going to make it a little bit bigger. So this one here is something that we cannot go any further. Or something you can see here, 1 equals 0, false. We're trying to prove false, which doesn't make sense. Okay? So I'm going to copy this guy here, just right here, to go over with you a bit, and then we're going to study that a bit and see how we can fix it. So here we have some outstanding unprovable sequence. Okay, let's copy that over here so we can see that. So we got green not equal to red. And also we got ML, TL. The traffic lights on the mainland side is equal to green. Also we got IL, TL, the traffic light on the island side equals green. Given these hypotheses, we want to prove 1 equals 0. Okay? And as side notes, do you guys remember what will be the only circumstance that can make an implication false? What will be the single row? True implies false. Remember? Okay? Okay, this one is also relevant, so that's what I'm putting here. True implies false, in is equivalent false. And the implication here, oh, let me use a slightly different color here. The implication, oh, that's not very good, sorry. The implication here is like the turnstile over here. So you can see now 1 equals 0 is equivalent to false right here. And true over here is something I'm going to show to you in the next page. At the moment, it is possible for the model to reach a state where both traffic lights are green. So that's why this true is also possible. So what it is saying is, the proof is suggesting for your current model, you're going to reach into some contradiction. Because you got true over here, which is feasible for your model, implies something that's false. That's a contradiction, which I'm going to show you more closely. All right, let me do a very quick recap so you wouldn't get lost when you study for this. So when you look at these two proof obligation, this one here and this one here. So somehow both of these is going to reach to a sequence that's going to look very similar. So if you look at the other one here, we are also going to get stuck on a sequence that has exactly the same unprovable sequence. Okay, if you look at both, they share the same unprovable sequence over here. And that one there tells you true implies false. True in the sense that I can show you a single trace of the model such that in that particular trace is going to lead you to a state where both traffic light is going to be green. That's true. And then we're going to get a false, which is 1 equal to 0. And overall, true implies false will be false. So that's the contradiction we have. All right. We cannot prove contradiction. Let's say you're doing this exercise yourself. You see that, okay, it seems like it is possible for the model to really reach a state where both are green. What will be the next step? You are supposed to come up with a trace that's going to lead you to such a state. But to really save the time, I'm going to show you exactly what a trace might be. All right? I'm going to show that to you. All right, let's now move on. So we got this contradiction here. We want to study a little bit further, and then we'll try to fix it. And that's another similar scenario that we cannot prove. So what we'll do is we're now going to look at this page over here. All right. So I set up everything that's relevant for you to look at. We got our model here. We got variables. We got all the invariants. We got ML out. We got IL out. You can see ML out is relevant for this one here. And IL out is relevant for this one here. All right, so I'm going to do one of them. You can do the other one as exercise. Let me now focus on the IL out. So I'm going to look at IL out over here. So let me use a different color here. IL out over here. IL out. Okay, I'm going to look at that. And for the ML out, you're going to look at that, how the contradiction happened as exercise. That's an exercise for you, okay? Let's now look deeper. So this is the sequence that's unprovable that we just look at. And this is the trace I give to you. Presumably, that's something we should really come up with, spending some time. But let's save the time. I tell you, this is sequence. And when you look at this particular sequence over here, it's saying that we have some initialization, and the capacity is simply 2. And then we got some MLTL green, ML out, ILN, and the ILTL green. After these two, you can see now both lights have become green. It is certainly possible. Actually, some of you already pointed out the possibility before the break, which is good. All right, let's pretend that's the first time we're learning about this. So what you will do is we're going to isolate this block over here. So you can see right here, we got both lights being green. So it's definitely possible. So that's why for this particular sequence here, for both lights to be green, it certainly can be true. Okay? But let's look at the next one. IL out is the events that I want to illustrate to you about a contradiction, IL out. Okay, so I'm going to look at IO out. Okay, by IO out occurring, we are actually going to just remember what IO out is supposed to do. IO out is actually going to be some events representing the car going to the breach. That one there is going to increment C into C plus 1, as we know. So you can see IRL here is going to increment the C from 0 into 1. All right, over here. And then I'm going to circle this. So C here is actually 1. At the same time, you can also see the two lights are simply green. All right, so this is definitely a possible problematic state. I'm going to write a. So this is a possible state. All right, and now I'm going to show you the contradiction. The contradiction would be if I go back to this invariant formulation here, where I can find everything that's available to me. Specifically, I'm going to look at this particular invariance. This one here. Okay, let me circle that. If you look at this particular invariant here, all right, let's now take a look. This one here is an implication. It says that C will be equal to 0 if I know MLTL is equal to green. MLTL indeed is green. All right, so now I'm going to highlight this part here. MLTL equals green. MLTL equals green. By modus ponens, I know C equals 0 should be true. Okay, I'll recap, but hopefully it's still kind of following. Okay. So give me one moment. Okay. So this is the part that's actually true. Okay, we got C equals 0, that's true. And also we got C equals 1, also true. So now we are in a state where C equals 0 and C equals 1. False. How can a variable be equal to 0 and 1 at the same time? So this is the contradiction. Okay, before you ask any question, let me recap very quickly. So we start with these two sequences that are unprovable. And when we try to prove each one of them, we're going to end up with an unprovable sequence like this. That one tells us it is possible to have a true state, which means possible states, where both lights are green. Indeed, we have shown that to you. For example, this state here, after IO out. In that particular state, we're going to have some contradiction. And the contradiction we have, 1 equals 0, is exactly the 1 and 0 we have over here, right? They are equal to each other, right? So you want to look at this particular state here. C equals 1 is point number 1. And point number 2, how do we show that C is also equal to 0? It's because the invariant tells us C will be equal to 0 if MLTL is equal to green, which indeed is the case. MLTL equals green over here. So we show that C, the same variable, equal to 0 and 1 at the same time, which is false. All right? It's a tricky one to see. But of course, to really come up with the trace and also the insight, it takes some time. But I'm just telling you directly. Okay? So when you study for this, really try to get the big picture right. Start with the unprovable sequence and see how this trace is really showing this particular state, showing the contradiction. That's your focus when you study for that. And then do exercise about showing that we have a contradiction as well for this particular one, for this events, ML out. Okay, I'll leave that to you. Okay. Question? All right, maybe not now, maybe later. Okay, let's now move on a bit. I want to cover just a little bit more and then we'll finish for today. How do we fix this? So there will be two fixes needed, turns out. Okay, we'll talk about fix number 1. I'll talk about both at the same time. Fix number 1 will be we need to add a new invariance. Okay, so far we got 4 of them, and we got to add a new invariance. And turns out this invariant corresponds to requirement number 3, which you can look back, is about the bridge being one way. We want to say either side of the light should be red. It cannot be both green at the same time. All right, that's really important. That kind of corresponds to some of you's concern before the break. That can address part of it. All right, so this will be the new invariance that we want to add to our model. All right. By adding this new invariance to our model, now you want to imagine this. Before we look at this, right? You want to think about adding an invariance. How is it going to impact the proof obligation that we already formulated? For example, when we started with this, we know that that one is unprovable. Somehow we want to fix the model and regenerate this particular proof obligation. Now, by adding a new invariance, how is it going to impact the regenerated proof obligation? Is it going to change the hypotheses, or is it going to change the goal? That's something you want to think about. All right. In this case, since we are adding a new invariance, you should really add a new hypothesis over here, because the concrete invariance is part of the hypothesis if you look at the proof obligation. All right. So sometimes in the exam, I may not directly ask you to really give me the regenerated proof obligation. I may say, now, imagine that I add a new invariance into my refinements as a fix. How will the new proof obligation look different? You can tell me exactly where the difference is. In this case, since we are adding just a new invariance, so the difference is just right here. That's the only difference. I'll make a note here. This is the only difference compared with the same proof obligation. The proof obligation without the change. Okay, that's the only difference. We have added a new invariance. Okay. And similarly, if you try to regenerate this particular one, right, which was also unprovable, you will see that you just need to add a new hypothesis as well. Okay. Yeah, question. Say it again, sorry. Both lights, both lights can be red. That's okay. That simply means no cars. We just want to avoid crashes. We don't care if both lights are red, in which case no car can really pass. At the moment, that means no crash can happen. Yeah. Yeah, think about invariant itself is really for safety. So we want to ensure safety. Yeah. All right, so now we got this new proof obligation here. And of course, you were going to try to reprove it. Okay, let me now guide you through very quickly. Okay. What's going to happen is the same as before, this guy here. And then you can see we just have added the new invariance all throughout. All right, all throughout. And the same step as before, right? Just the new invariance, all as before. And when we get to this particular unprovable branch, but now we have this particular one added. So this is going to make the proof work. Okay, I'm going to talk about it as the last bit for today, quickly. And I have copied this guy here into here. All right, let's see how we can prove it. I'll give you some guidance over here. And there are multiple ways to discharge it. I'll give you some hints. First of all, I'm going to focus on this particular invariance that we just have introduced, which is a new hypothesis, like an extra hypothesis. As you can see, this one here is an OR, disjunction. So I can apply ORL. All right, that one there is going to be, okay, so I got something there on the top, which will be green not equal to red. MLTL equals green. And also the left, which is MLTL equals red. and ILTL equals green. Turnstile 1 equals 0. So that will be the first sequence. And then there will be another one which I'll leave as exercise for you. I'll do the first one. Okay, think about this one here. It's going to correspond to this particular disjunction, right? That one there will be exercise for you. Okay, and then over here you can see we got some equality. This one is some equality. Okay, we can replace MLTL by green, basically, right? So that will be EQLR and monotonicity at the same time. So EQLR, EQRL is the only one you can apply monotonicity at the same time. Okay, but other than that, you should really do one step at a time. So that one there is going to be, let me put it down. Okay. So it will be, again, green not equal to red. And also, this one can be dropped right after. Okay. So MLTL is replaced by green. Green equals red. ILTL equals green. Turnstile 1 equals 0. And this is something I would like to pause and then going to give you some hints. There are two possible ways to go forward. You can try. Okay, I will encourage you to try both. Approach number 1. You can focus on, let's say, this one here. This is a negation. So approach number 1, you can try. Approach number 1, you can try the new rule that we talk about today, not L, to go forward. Okay, I'll let you try. Once you apply the not L, it will be very obvious what you're supposed to do. Approach number 2, you can focus on this one here. This one here, if you refer back to the definition for green and red, because both are members in the same set, since there's no duplication in the set member, so they should be, this one here, they are equal, should be false. All right. So this is also something you can try. Approach number 2. You would say green equals red should be equivalent to false. And then you can go from there. Well, actually, that should be quite obvious what you're supposed to do, right? If they are simply false. Because false implies anything, right? So either approach number 1 or approach number 2. Approach number 2 is very obvious, but try approach number 1 as well. That might be a good exercise for you to try the new rule. Okay, let me just take 30 seconds. I'll stop here, but for next Tuesday, it will be the last class, and we are actually going to look at about the fixes for the traffic light problem. And then we're going to look at maybe a few more aspects about the second refinement, and then we are done. All right, so I will see you next week.